Okay, so here's the solutions for the problems from today. First one says the phosphorus acid H3PO3 is actually a diprotic acid with a Ka1 at 1.0 times 10 to the negative 2 and a Ka2 at 2.6 times 10 to the negative 7. The question is asking what are the values of the concentration of hydrogen, the pH, and of the HPO3, which is the ionized phosphorus acid, if you have a 1 molar solution. Okay, so let's take a look at a couple things real quick. Okay, so first things first, we got to understand one thing. If you take a look at the Ka, right, 1 versus the Ka2, right? This is to the negative 2 and this is to the negative 7. So you can see that Ka1 is really a lot bigger than Ka2. And because this is so insignificant, right, the negative 7, that all the values that we're going to get are going to be from the Ka1. Because by the time we get down to numbers that small, their contributions, again, are negligible. Okay, so let's go ahead and let's write the equation, right? So we're going to have H3PO3, right? That's going to react with the water. All right, remember the water doesn't play a role, but I want you guys to have it in here just so you guys can see. And then we're going to do the first ionization or the first removal of the hydrogen, right? So that's going to be HPO3, and that's going to have a negative 1 charge since it got rid of one of the H's. And then we're going to form that H plus, okay? Okay, so here's where we're at, right? We know that we're in a 1 molar solution, all right? So again, we're going to do our ice chart. All right, so let's go ahead and plug in our numbers. So the initial concentration right here is going to be 1.0 molar. We're going to leave the water alone. And then here is going to be 0.0 and 0.0. This should all be the same. This is going to change plus x, minus x. And this is going to be x, and this is going to be x. And then when you add everything up, it's going to be 1.0 minus x, and then this is going to be x and x. Now remember that these are being added, okay? Now, when we're working here, what we're seeing, right, is the ice chart in the equilibrium, right? So let's take a look at what we got set up. Okay. So here, again, remember that we can neglect this one. It's negligible contribution. Even these are pretty small, but we know how this works. We know that the value of the Ka is equal to 1.0 times 10 to the negative 2, right? And then that's going to be equal to our constant, which in this case is going to be x squared over 1.0, right? Okay, so let's scooch over this way. Let me see here. If I have that the Ka is equal to 1.0 times 10 to the negative 2, right? And I multiply that by the 1, then I'm going to be equal to x squared. Therefore, if I have that x squared is equal to 1.0 times 10 to the negative 2, and I take the square root of both sides, right, I'm going to end up with x is equal to 2.1, right? Now we know the value of x. Both of these represent x, so then we know that the molar concentration of hydrogen is 0.1. If we take the negative log of 0.1, right, then we end up with a pH is equal to 1. So there's our pH. There's our pH, right? So one of the questions was asking me, what is the concentration of hydrogen? That's right here. And then the other question was asking me, what is the concentration or the pH of that? And the pH is right here. Now, here's where it gets a little bit tricky, right? It's asking you for the value of the HPO3. So this is when this happens, right? Let's scooch over this way. So the first reaction that we see is H3PO3 becomes H2PO3, right? 1 minus. And then the one that comes after that is the H2PO3 becomes HPO3 2 minus, right? Now, this has a value of a Ka. This has its own Ka, right? Which was the 1.0 times 10 to the negative 2. And this has its Ka2 at 2.6. Times 10 to the negative 7. So this is what I meant earlier, right? If you take a look at these two numbers, these are drastically different. And you can clearly see that the Ka2, right, is a lot smaller. So all the contributions that this hydrogen is going to have, right, or this acid is going to have in terms of hydrogen is going to be really, really small. You can see its ionization constant here, right? So based on this, then the ionization or the ionization constant, the Ka2, is going to be the value for the HPO3. So at this point, let me erase this here. HPO3 2 minus is just going to equal whatever the Ka value is going to be, which is times 10 to the negative 7. All right. So that's the solution for question number 3, I believe, on your work today. Okay, so let's move on to the other one. The other question is asking when 50 milliliters of a 0.10 formic acid is titrated, solution is titrated with 0.1 moles of sodium hydroxide, what is the pH at the equivalence point? What would be a good range for an indicator solution, and what would be the best indicator to use? So right off the bat, I already know that this is not one of my lists. So I know that formic acid is a weak acid. So that equals a weak acid. So our titration is going to be a weak acid with a strong base. Now, based on my curves that I saw the other day, right? Sorry, strong base. I know that this equivalence point, right, is going to be right above 7, so it's going to be slightly basic, okay? Okay, so let's get this one started. Let's start with writing our reaction. So we're going to have H2CHO2. Let's see, correction. HCHO2. Remember, formate only has a 1 minus charge. That's going to combine with sodium hydroxide, and a result is going to form NaCHO2 plus OH minus. Now, remember that formic acid is a weak acid, right? So because it's a weak acid, it's not on that list, it's going to hydrolyze with water, which means it's going to react with water and it's going to form this salt, okay? So that's where it's going to be a little bit different, okay? Okay, now other than that, everything else is going to be pretty much the same. We're going to take a look at our ice chart, okay? And we're going to get that set up. So ICE, okay? Now, we said here that we have 50 milliliters of 0.1 formic solution, formic acid. So let's go ahead and figure a couple things out, right? So our starting value, right? Let's go aside over here and let's take a look at our formic acid. So we have 50 mLs at 0.10 molar, okay? Now, if we convert this to liters, that's going to give us 0.050 times 0.10 molar, which gives us a value of 0.0050 moles, right? Okay, so this is our starting amount of moles of the formic acid that we have to neutralize, all right? Now, we're looking for the equivalence point of the NaOH. So what that means is we have to figure out how much of the NaOH we're going to add to neutralize 0.0050 moles of acetic acid, right? Now, we have a molar concentration of our NaOH. So our molar concentration of NaOH is 0.100 molar, right? Now, what we need to do is we need to figure out, okay, I need to create 0.005 moles of NaOH, right? And I got to know how many liters that's going to take to add to the solution, right? So remember that to find the liters, right, you take the amount of moles and you divide it by the molarity. So in this case, it's going to be 0.005 divided by 0.100. So that's going to get me at 0.05 moles. Sorry. Milliliters. Excuse me. Or liters. Okay? Okay. So if I convert this to milliliters, right, 3 times, that means I'm going to have to add 50 milliliters of the NaOH to reach the equivalence point. So if I have my analyte here with an initial volume of 50 mLs, right, and then I add 50 more mLs of the NaOH to reach the equivalence point, well, now I'm sitting at 100 mLs of total solution, right? Okay, so now what we're going to do is we're going to calculate that molar concentration, right? Okay, so what we're going to do is we're going to take a look at our molarity. If we know that we have 50 milliliters added to the original 50, we have a total of 100 mils, right? We still have the same number of moles because that's the number of moles that we needed to neutralize that acid, right? So if you take a look at the molarity and you calculate 0.005 moles divided by the 0.1, then you're going to get kind of right back where you were. So your molarity is going to be equal to 0.05. Okay, so that's where we're at right now. Let me take this up a little bit. Okay, now here's the difference. Okay, this is the reaction that's happening where we would set up our ice, right? However, what's going on right now is we're forming in this salt, right? So we're not going to use the Hasselbalch equation, right? Which is the pH is equal to the pKa plus the log of the anion over the acid, right? We're not going to use this one because we're not in the buffer zone. We're past the buffer zone. Now we're at the equivalence. And what's happened is this salt has now formed, right? Because for every mole of acid that we neutralized, right, with the strong base, we've had a formation of this salt. So we're going to rewrite this. And I wanted to illustrate the difference for you guys. But here's what we're going to write, right? So in this case, we're going to end up with our formate ion, which is minus, okay, our water, and then we're going to see the NaOH, CHO2 formation plus the OH minus, right? So remember that the Na and the OH are coming from the strong base, but what we're looking at is we're looking at the interaction between our acid or our formate ion and our Na to form this salt, right? So then from here, this is where we're going to get our starting value, right? Because this is in molar. This is in molar. So initially, right, we're going to have 0.05 molar, right, of this one. We can neglect the water, right? And then here we're going to have 0.0, 0.0. This is going to reduce by x. This is going to increase by x. This is going to increase by x. And at equilibrium, or the equivalence point, we're going to end up at 0.05 minus x. And then this is going to be x and x, right? Now, the KB for the formate ion, right, is equal to 5.6 times 10 to the negative 11, right? If we set that equal to our mass action equation, we're going to end up with x times x. Remember, we can neglect this one over 0.05, right? If we multiply 5.6 times 10 to the negative 11, and we multiply that by 0.05, we're going to end up with x squared. If we simplify this, we're going to go 1.673 times 10 to the negative 6 is equal to x squared. Take the square root of both sides. So then x is going to... Okay, let's see. Okay, sorry guys, I have my notes mixed up. I try to do these beforehand so I don't waste your time. But here's what's going on. If you multiply 5.6 times 10 to the negative 11 times 0.5, you're going to end up with, where is it? 2.8 times 10 to the negative 12, right, is equal to x squared. Sorry about that. Okay, so here we are, right? Now, we take the square root of this, and we take the square root of this, we end up with x is equal to 1.673 times 10 to the negative 6, right? So now we know, right, the concentration of our salt, right? Now we also know the concentration of the OH because x is equal to this amount. So if I take the POH is equal to the negative log of the concentration of hydroxide ions, then I take the negative log of 1.673 times 10 to the negative 6, right? And I'm going to end up with, let's see, 5.7765. So this is my POH. Remember that pH plus POH is equal to 14. Therefore, my pH is going to equal to 14 minus 5.7765. And that's going to leave me with 8.22 is equal to the pH. Right? So in this case, because it's a weak acid, we have to use the processes of the salt, right, to calculate the pH. In this case, we had a Kb to work with, so we ended up using the pH plus POH is equal to 8.22. I apologize for the mishap as I have my notes all over the place. I was trying to do them after school, and but here we are. Now, the other part of the question is asking you what would be the best indicator to use given the endpoint and the pH. So now we're going to take a look at our charts here, right? We can take a look at our chart. Now, this is what you're going to see on the AP exam. They're going to give you a bunch of different indicators. You're going to have to calculate the pH and figure out which one would be the best to use. In this case, we have about 2 right here that would work perfectly, right? Because they're within the range. 8.2 to 10.0, and then 8.0 to 9.6. Now, because our pH at the equivalence is 8.2, you want to have that kind of right in the middle of the range. So based on the acids that we have here, right, and the endpoint is at n.1, I would choose the Thymo Blue because that's perfectly within our range. All right. So the best indicator to use for this particular titration would be the Thymo Blue. Remember, you want your indicator to be at or near the equivalence point. So this is right within the range. All right, guys, those are solutions. Thank you.